but yeah, so yeah, so today we're lucky to have Robin here to answer questions about latent diffusion and stable diffusion and uh, other I guess all the other research he's done as well. And yeah, we talked about latent diffusion and stable diffusion last week. So yeah, it was pretty interesting to finally dive into those papers and discuss that. Um, yeah, I guess you know folks can of course unmute themselves if they want to ask questions or put in the chat. But I guess I'll start with a few questions I have, and then I guess later people can also ask questions. I guess I'll start out with maybe just a general question, which I mean, I all kind of know the answer already a bit, but I think it's good for the rest of people to know to also hear about it. Is just kind of generally how was latent diffusion developed, and also how did the stable diffusion come into how did stable diffusion get created? Yeah.
um, yeah. So for us, it was kind of, I would say, a natural step because, as you might know, we did like this VQGAN stuff before, where we kind of did autoregressive modeling with transformers in latent space, and the goal always was to kind of really use this to actually get natural looking images out of the model, right? So with VQVAE, which was like the established method before, was always looking a bit blurry because was usually just trained as a like with a reconstruction loss only. And so you could clearly see that this stuff had potential, but it also didn't really work. So yeah, this was actually where I spent like most of my PhD kind of research with. And then this was like right after VQGAN, we actually did a work on, so we saw the diffusion literature popping up, and then the first one that we did was actually, it's called ImageBART, which was kind of a hybrid. So we're still in discrete space, and we kind of used a very short diffusion process in discrete space, a multinomial process, like with 4 or 8 steps, and then modeled each of these steps with an autoregressive model. So we still need like a powerful generative model to actually model these very. It's not like that. It's that you can model it with a Gaussian assumption, like in diffusion models. And yeah, that was still in discrete space, but this was kind of the natural transition to then actually try, or let's say, okay, let's just try diffusion models, like Gaussian diffusion models for this. And we ran some initial experiments on landscape generation conditioned on semantic maps, which is like, if that it's like super simple experiment. You don't really need much compute for it, but we immediately saw, oh, this produces really good looking results. It has like these nice in-painting properties and so on.
And that was just with plain Gaussian distribution without the autoencoder, or is that was already with?
Oh no, that was already with the autoencoder.
Okay.
Yeah.
Cool.
Yeah, exactly. But this got us like excited, and then we just launched all different kinds of conditionings for the models. Text was there kind of from the beginning. We didn't know about classifier-free guidance for a while, which was a bit unfortunate. I think it would be actually interesting to look at the checkpoints that we trained very early on and just apply classifier-free guidance to them. I'm really curious how they look, because we always sampled them either with like classifier guidance, which was more popular at this time, or just like with a classifier-free guidance scale of 1, so no guidance. And yeah, I think it would be interesting to actually look at these results without with classifier-free guidance applied, especially for text to image. Yeah.
And this is around the end of 2021, right?
Yeah, that was like in summer 2021. We then published a paper the end of 2021 simultaneously with Glide. It was on the same day actually, and it was like so related. Like the methods were extremely similar. And yeah. We were kind of a bit, to be honest, a bit frustrated because it obviously got more attention. Yeah. But then, maybe that's also a good way to explain how Stable Diffusion actually came to be, because we then got more compute in our research lab, actually. So before that, we trained each of these models on a single A100, which is nothing, actually.
Yeah.
And then we got like a HDX machine with 80 gigabyte A100s, and we trained like on all of them. And we then got like this latent diffusion model that we published in April, text to image model. And this was already pretty impressive, I think. So there we also used classified free guidance for the first time, and it was like, oh wow, this stuff really works. Was that 256 by 256 resolution, so not quality is still not too good, but we really saw, oh, this can work if you scale the training a bit.
Is this the 1.45 billion parameter model
Yeah,
in the paper?
exactly. That's the one.
Okay.
Yeah, exactly. And so from that, I was pretty confident that this would work even better if you would scale more. I wanted to train it at higher resolution all the time, but that wasn't possible with the compute, because if you then go to 512, what we did with Stable Diffusion, you just need way more compute to kind of fit the same batch size. And yeah, luckily we stumbled across Imad, who agreed to do this. And we basically just took the same architecture as before. The only thing that we changed was we changed it, like the text encoder, to a frozen one. We use Clip instead of training it jointly with the model. But that's basically the only difference. And then we also trained it on higher resolution, not on 256 by 256, but on 512 by 512. But these two things are basically the only differences.
And what was the reason that you used a smaller model size as opposed to what you had in the paper?
So the UNet is basically the same size. It's only about the text encoder.
Oh, okay. Okay.
So it's basically really just the same architecture.
Okay.
Just with the text encoder replaced.
Okay, that makes sense. Okay. Yeah. And yeah, I guess the text encoder trained jointly, that seems to do quite well. Do you think that that's a good idea, or it's always just a better idea to use a pre-trained text encoder from the start? Or maybe even like fine-tune the pre-trained text encoder during training?
Yeah, it's an interesting question. I ran some experiments with it, and then looked at the FID scores, and they were always worse.
Okay.
And then I discarded the idea, but maybe it would be nice to actually look at it again. So a very nice property of the first LDM was that it was rendering text, like legible text that made sense. So it's probably a combination of this training method, like the data that we trained on, which was Lion 400M, which contains lots of text actually in the images, and also like the tokenizer that was used with the model. So yeah, maybe a combination of a of like a learned encoder and a frozen encoder might work. I don't know.
Yeah, I just thought I'd just share these pictures again to remind folks who may have not seen them. But like, yeah, I find this pretty interesting that the text was actually quite good. I mean, I feel like this is pretty comparable to some of the even the current models that are circling around right now. The text rendering is pretty good. So yeah, I think definitely there seems to be a lot of potential, I guess. So we'll see. Yeah. Yeah, I guess we've seen still a lot of autoregressive models do well, with Party and I guess even some of these later ones. Do you think that it seems like you've gone all in on this sort of diffusion and yeah, this approach. So do you think there's any potential for like hybrid approaches or the autoregressive is I guess also comes down to maybe why you decided to go all in on diffusion and yeah, your reasoning behind that as well.
I think diffusion has a few nice properties if you do image generation. So you kind of can choose how many steps you want to do. Cannot really do that with an autoregressive model. You can do image modification very easily. You have image to image or SD edit, whatever you want to call it.
Right.
Which is supported out of the box. Image inpainting, like in a naive fashion, is also supported. So these are pretty cool properties which just make it more suitable for image synthesis and image modification, I would say. But I think hybrid approaches, especially in a multimodal setting, are really interesting. Yeah, I think maybe like generating a coarse context with a diffusion model or some kind of discrete diffusion model and then doing local autoregression might also make sense, especially if you train on multimodal tokens. So I would actually be interested in training like a large multimodal model in tokenized space. So you have like VQGAN tokens, but you could also have some audio tokens, some text tokens. I think this would be interesting. Yeah. And then the combination of autoregression and discrete diffusion might be quite interesting. I think people are looking at this for NLP.
Yeah. Well, I've seen also like VQ diffusion and things like that, which also seems very interesting as well.
Exactly. Yeah. Exactly. That's what. Yeah.
I think I know that I think Boris is very excited about this sort of work in terms of like VQ diffusion, and he's interested in exploring that a little further.
Yeah, and then we have kind of the mask GIT line of work, which is somewhere in between, maybe, I don't know, and the recent newspaper.
Yeah, we were just looking at that earlier. Jeremy and I and Jonathan and Pedro. Yeah, that's a very interesting paper as well. So it seems like there's a lot of interesting directions there. So that's why I was just kind of interested in your take on those. So does anyone else have any questions or comments or anything? Oh, someone asked, why do you think? Nev, why do you think sequence order matters so much for image modeling, especially for VQGAN?
I actually don't think it matters that much. Or is there evidence that it matters much? I think it's very unnatural to actually model an image from the top left to the bottom right. Or maybe, yeah.
I don't know.
We actually tried some experiments.
Oh.
Yeah, sorry.
Different factorization orders.
He muted himself. Not sure what happened.
So we tried some experiments with other orders. I'm not sure we came to a conclusion. Another interesting one would be to train on all orders simultaneously, but then it's obviously probably much harder to train. But yeah, for images, it's kind of unnatural to do this, right?
Yeah, if we had some model that could just take randomly shuffled sequences, model that, we could just experiment with that and see which one's better.
Yeah. So I think we could do that. Yeah. You could even train on all of them simultaneously, right? But then it's probably harder.
Yeah, actually, I'm writing code for that right now.
Oh, nice.
So yeah, I'll write back how it works.
Okay. Do you have any results already?
Well, I managed to overfit a single image, but not on any actual dataset yet.
Yeah, we'll see. Yeah.
Any other questions? I mean, if no one has other questions, I might ask some more, let's say, I guess some specific questions about like code and things, and I guess loss functions and stuff like that. I guess one question that we had come across when we talked about this last week was it seems like the sort of, let's see here, the autoencoder model loss function, which I'll just share my screen here, is this this is maybe not necessary. Is this I think the code does use something different. Is that right? In terms of like, I guess one part we were confused was like, if this L adversarial, is that just the loss for like the 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 generator or
yeah. In this
okay.
formulation, it's just the loss for the generator.
Okay, because in the VQ-GAN paper, there's also a L-GAN, so I thought it might be the same, but then that's why I was confused, because you have the L adversarial, and then you also have your log of the discriminator, and so I was confused. I thought, oh, is this supposed to? Why isn't that covered in the L adversarial? But maybe they're supposed to be.
I think this equation 25 should just be like the full minimax game kind of between the autoencoder and the discriminator. But yeah, so just from seeing that, I actually don't really remember. Maybe we also messed something up, but I would say this is just the generator loss function, and then it's so to be clear, it's the same loss as in taming transformers, right? The only difference is we have like for latent diffusion kind of these two different autoencoding models. One is based on this VQ-GAN, and the other is not using a discrete bottleneck, but a continuous one, which is regularized with a...
Right, so the only difference is this term then.
Yeah, so this is either a kind of codebook plus commitment loss, if you have a discrete one, a discrete bottleneck, or a KL regularization.
And then yeah, so that would be this this is the codebook loss, and then okay, so that's the codebook loss, and then this would be the GAN loss. What is the reasoning behind, I guess, using this sort of adaptive weighting? How does that help the trading?
That's a good question. So initially, when we didn't have that, it's kind of hard to find the right weighting of the adversarial loss, at least the way we implemented it. So you have some like that. This really took a long time to find a good weighting without this adaptive factor, where you, I don't know, I think it was around for a very specific setting, so probably not, doesn't generalize, but it was around 150 or something, and this just weird. And then someone came up with this, yeah, which where you don't have to look for for weird weightings.
Just to keep the sort of scale between the reconstruction loss and the GAN loss about the same.
Yes, exactly. Yes.
Okay. And then in the code, I think we noticed there was some sort of like additional term in the, I think it was in the reconstruction loss. There's like this log var and this sort of NLL loss.
Yep, I think we disabled that.
Oh, okay. Kat was also saying something about like another sort of, yeah, there's some other value that was being predicted and used in this NLL loss that we weren't really sure what was going on there.
That would be the log bar, which kind of gives you a weighting between the KL loss and the reconstruction loss. Okay. It was introduced in a paper that's called two-stage VAE. Okay. I can share that. A link to that. Yeah, but we I think we somehow abandoned it for this one because
so that's not used in the...
just, you know, it's not optimized. So this is like another parameter that you could add to your optimizer and optimize, but we didn't use it for this paper. You would be interesting maybe to get it back. but we were kind of really just optimizing for high reconstruction quality, and that was it.
Okay.
So, let me share a link to this paper. This might be interesting if I find it. Yeah, this one.
Okay. Diagnosing and enhancing VAE models. Okay, cool. Yeah. I think those were the main questions I had about, I guess, with the details. Yeah. There may have been in the stable diffusion. I guess the charts. There was a sort of evaluation over here, I think, where I guess not this one. This is the comp weights one. I think it was in the stability AI one of the new 2.0 models, where I think you were comparing the 768 model with the 512 models or something like this. Yeah, was it this one? Yeah,
I think
so
I think that's only the 512 model, right?
Okay, these are all 512. Okay.
Yeah. Because otherwise
Okay,
you get
yeah,
like,
I think that's the confusion that we were having. It's like because V 2.0 usually is referring to the 768 model, right? Or I guess yeah, one of the models that are being listed here, I guess.
It's the 512 model. I think it also says
Okay.
512 samples. Yeah, it's a bit like, I mean, you can also sample the 768 and then rescale, but then you kind of have these artifacts from rescaling in FID, and FID has some very, very weird properties if you do that.
Right.
So yeah, so for that we just compared the 512 models.
Okay. And then it seems like the FID of the V objective is slightly worse.
Yep.
Right? What
Yeah.
Is there any do you have any intuition behind that?
I mean, it's kind of consistent with all your other observations that were made with DDPMs, right? So epsilon objective is kind of very well suited for if you reweight like this L simple formulation where you kind of drop the first few steps or weigh them very low, where you predict the noise in the diffusion process, kind of produces the best FID. And I think we still see that here, although it's in latent space. So
okay,
the
that's interesting. Because
yeah,
I thought that my understanding was like the V, like because it gives that sort of sort of a normalized range that it produces, right? So it should be easier to at least like if there's error, it should be, I think it deals with any sort of error a little bit more nicely or something like this, if I remember correctly. Kind of the similar, I think there was a sort of similar thing in Karas Hotel.
Yeah, that's right.
So that's why I thought it would be better, but I'm a little surprised to see that it's worse.
I mean, FID is also not perfect, right? So, so I don't know. I think like this difference is not too important actually, but that's just my opinion. I don't really like FIDs. Like, it gives you some form of signal, but I wouldn't draw any conclusions from having like a 1 point difference in something.
Okay, yeah.
Because
do you have any
has
sort
so
of
many
metrics
glitches
that you like?
Looking at the results is
okay.
best. Or
yes.
having multiple people look at results, I think, is even better.
Okay.
So yeah, some form of human evaluation is
right.
It gives you some idea, but it's, yeah, I don't know. It comes with so many eventualities, and I saw so many weird things with FID that I do not really trust it. So yeah, I don't know. It's but just my opinion.
And that's even like within your own experiments, like comparing between your own experiments, you'd still feel like it's
So
a little
if you
bit
have like
hard.
if you have a very different curve, then that gives you some signal. I think that's true. But if it's very close, then maybe some other metrics might be better.
Do you think it has maybe to do also the fact that I guess I don't know exactly what data sets you're testing on, but I guess the problem is like FID is using, the sort of network that is trained on
Yeah,
image
exactly. Yeah,
management. So
yeah,
there might be some distribution shift. So wouldn't it be just better
yeah,
to have your own classifier?
yeah.
At least that's the sort of things we've been doing with our own experiments for like fashion MNIST. We use our a fashion MNIST classifier and
Oh, nice. Yeah, yeah. I think that's good. Yeah, yeah. I think that's good. Yeah. In a more recent paper, we did some a colleague of mine implemented clip FID, which is probably better. Yeah, I think that's good. Yeah, should probably just switch to that by default.
And I guess the experiments you're usually starting out with like a smaller data set. Like I think maybe you've mentioned to us privately before, like ELSA and things like this.
Yes.
Or
Yes.
okay, so even now you're just mainly starting out with those sorts of smaller data sets, and
So
before moving up to
text to image, you can do CC like 12M conceptual captions 12M, for example, something like that, which is not very small, but smaller than Lion. So
yeah.
it's so you can do you can do the 3M or 12M version. Yeah, so 3 million or 12 million.
Interesting. Yeah, I guess again, open up the floor to any other questions that people may have. I guess yeah, someone's asking about where to from here. From a research perspective, what excites you currently?
A few things. One of them is how do we actually make better use of all the data that we have. So because when we trained Stable Diffusion, we did like this multi-stage training. In the first stage, we kind of trained the model on 256 by 256 resolution, didn't really care about the data. But then we went to 512 by 512, and then we dropped all the images which had like a native resolution, which was lower, and we also introduced some aesthetic filtering. So we used some aesthetic prediction model to kind of remove the images that have some low visual aesthetic value. And this filtered the data set quite a bit. And from that, I mean, you lose some information if you do that. And I think there might be better ways to do that. So this is something that I'm interested in, just in using as much data as possible while still having these kind of levels of control. What are other interesting multimodal models? Other modalities are super interesting. I also want to investigate a bit the properties of if you distill a model and have a few step model. How is it different from a full diffusion model, right? From a fine tuning perspective, what else do you? What kind of properties do you lose? Yeah. How do you measure the aesthetic value? So this is based on a Lion. No, what's the name of the official name of that model? A few people trained
bot.
Yeah, exactly that one.
Simulacra aesthetic captions.
Do you want to say something about it?
Oh, I was just sort of labeling that. I guess they had a bot in like I think a Discord server where they were labeling generated images and people were labeling the aesthetic. I guess they gave an aesthetic ranking or something like this. And then afterwards, they trained a model to predict the aesthetic ranking that people were labeling. So it was a fairly simple classifier. I forget what kind of classifier they used actually, but it was pretty simple.
I think it's based on clip embeddings, very simple.
Yeah,
Maybe
I think
just
it's
a
just like a
small
progression
MLP.
on clip. Yeah, some sort of small MLP on top of a clip embedding. Yeah. So or yeah, it
So
was like a never saying I think it was a linear SVM. Yeah, it was a very simple architecture.
oh,
so,
I see.
yeah.
Okay.
But I think it was still based on clip embeddings though, right? It was like a linear
Yep,
SVM on top
I
of
think
clip
so.
embeddings, something like that. Yeah. So that's how they got the aesthetic captions or aesthetic ranking. Yeah.
I think there was even some kind of feedback loop, if I remember correctly, where we kind of had the first version of the model, which still was used to produce ratings.
Yes. I remember something like that. Yeah.
So
yeah, like they had it kept including different. I think it's they even started out with like DQGAN clip models and those images, if I recall correctly.
Yeah.
And then some of the latent diffusion and those sorts of models started getting in there as well. So it had seen different types of generated images as well. Yeah, it's very interesting.
Yeah, but obviously improving that, or maybe getting it more a bit more complex than just a single scalar value that kind of judges the aesthetic value of an image. I think this can also be a very good signal. Yeah. How many attempts did it take to get the training to work? So I assume you're talking about Stable Diffusion. So this was kind of very messy training, where we, when something went wrong, we kind of resumed the training from the last best checkpoint and changed something to make it better. So at some point we also included some high-res data, some upscaled data actually. So if you do that, then your model learns to replicate upscaling artifacts, which you definitely don't want. And then, yeah, luckily people complained about that, and then we could tune it out of the model. But it was also for us, it was kind of a first experience how to do that. So yeah, it was like one large attempt with many readjustments.
Were there like lots of manual things like changing the learning grade in the middle of training and stuff like this? Okay.
Yeah, exactly. Yeah, exactly.
Seems like it's always a messy process when training these large models.
Yeah. At least like if it's the first time that you're training it. Diffusion bridges vector quantization. Actually, don't know the work.
Yeah, I don't think I've seen this one either, or have I? I'm not sure if I have. Nev, do you want to say a little bit if you've seen this paper, do you want to say a little bit about it?
Yeah, of course, I can send the link. So it's related more to VQGANs. Basically, the main innovation is that they somehow learn both the autoencoder and the prior during the same training run. And yeah, have you read that paper? Have you tried something like that? Do you think that's even useful?
I actually did not read it yet, so it sounds interesting. This so they're training it jointly, right? From your description. I always had trouble when trying to train these models jointly, because it's so difficult to kind of get very good reconstructions while matching some kind of prior. But if they manage to do so, I mean, that's super interesting.
So is this more like, I guess, kind of like the NVIDIA paper, but then with a VQGAN autoencoder? Is that what it is?
Oh, which NVIDIA paper?
Probably the LSGM paper.
NVIDIA had some sort of the sort of LSGM. It was like a latent space. They trained the latent space jointly with the diffusion process. But I think their autoencoder was like just a standard KL autoencoder or something like that. It was not VQGAN. So is that like the main difference here?
Yeah, exactly. They have like a continuous latent space. The difficulty with that is that you to get kind of good quality, you always have to have very large dimensions of the latent space. So yeah, I'm really not. It's super hard to get like joint training at a good quality. So it is, yeah. I don't know about the specific work.
Yeah. I guess I was going to ask like what you think about like this sort of the diffusion models for language and things like that, because of course people have been talking about this and talking about like, oh, maybe some of the sort of perceptual properties of diffusion models that make it good for images don't transfer as well to language, and maybe it's not as efficient. So I don't know what you have any thought, if you have any thoughts on this, and where do you see that sort of field going?
Yeah, and it's yeah. I find it very interesting. I mean, I don't know much about NLP actually, to be honest. Or like on a language specific level. I think it's my intuition is that it's difficult to define like some reasonable form of information removing process. Like in images it makes kind of sense what diffusion is doing. For language it's probably a bit more difficult. So one idea is maybe to map these tokens to some form of vector space and then do it there, but yeah, I think it's super exciting. There was a DeepMind paper I think in December which had promising results. And maybe combining it with autoregression, like having like a coarse diffusion process and then local autoregression. I think this is something that makes sense.
Right. Yeah, there was that. I think the paper is the one by Sander Dielman, he had that paper, and then, he had recently also wrote a blog post about this as well, which I think he was cautiously optimistic. I think it seemed that's the sort of tone that I saw. I was like, it sounds very
that's
very interested, but of course,
a good signal.
There's a lot of caveats he was mentioning. So yeah, it was interesting. Yeah, I think Jeremy linked to that blog post in the chat. Yeah, does anyone else have any questions? Any plan to do RL feedback on the diffusion?
I think people have plans, yeah. People have plans, yeah.
Yes.
So yeah, super curious how this goes.
I'll say a little bit about that. There's EleutherAI is working on this, so they're working on an instruct stable diffusion. So they've mentioned that publicly already. So it's still in a pretty early phase, but I guess that's all I'll say about that.
Yeah. But yeah, I think they're the right people to do that. So someone with experience in that kind of training. I think
going back to like sort of the distillation stuff, do you ever like, I guess right now you've got it down to like maybe it was about like 4 steps or something like this. Do you think it could be even lower than that? And also I guess in terms of like reducing these number of steps, do you think that distillation is better than some of these accelerated sampling methods, or worse? Because of course, like in both cases, they sort of change the sort of properties of what you're sampling. In terms of the distillation, you might lose some stuff from the distillation process, and of course, accelerated sampling can also, it has its own, sometimes can have some issues. So I guess, do you have any thoughts on which might be better in terms of fast sampling and while still getting good quality?
Yeah, I think it's a very good question. It might be the case that at some point you will have, like, let's say you do just pure text to image synthesis, and you might want to have a very fast model, maybe even with some adversarial training. So this, I can imagine. Like, so when I look at the at the samples of a few-step model, few-step distal model. They're kind of blurry, kind of have artifacts. Maybe you could use it as an initialization for an adversarial training, or you can even add it, because I mean it's cheap to evaluate, or it's kind of cheap to evaluate a 2-step or 4-step model at training time. So this could work.
Can you specify what you mean by adversarial trading? You mean like trading a GAN or something like this? Or?
Yeah, exactly. Yeah. Okay. Yeah. Or maybe even have like a full GAN for if that stuff turns out to work. For like just if you want to have very fast text to image synthesis, but for the other applications you might want to have a still a diffusion model, like image to image, image editing in general. And it's not that clear what else you use. Fine-tuning properties you probably also lose, because diffusion kind of provides a nice natural regularization. And then if you have very few data points, which is like a typical scenario in fine-tuning, then you probably I do not really know yet, but
when you mean
my hypothesis is that you then suffer from overfitting more easily.
Okay, so what do you mean diffusion is good for regularization? You mean like because you have these so many steps, so then when you choose a random time step, you've got like this variety to choose from during trading, so it look different even if you choose from the same image or something. You'll see different sorts of noisy images, I guess.
Yes.
Okay, and then if it's of course distilled, you'll have like say 4, and then if you choose from 4, you'll often see the same noisy image during the fine tuning. So okay, so then that would lead to overfitting.
Yeah, that's kind of the intuition.
Yeah, I guess I never really didn't think about that, but yeah, that's a good point. Okay, so like I guess for fine tuning, this seems like distillation maybe it has to be explored a little bit further.
Yeah.
I guess also maybe for like it seems like maybe some of these text to image models, text to video models may benefit from distillation in terms of like I know some of them start with text to image baseline. Yeah,
absolutely. If you just want to have like a text to video model, then absolutely I agree. I guess it's necessary if you want to have somewhat reasonable rendering times.
Yeah. I guess with distillation, you do go from this sort of like progressive distillation where you go like we have to keep dividing the number of the steps and things like this. Do you think there's any way of I guess speeding that up? And I guess this is from a trading time perspective instead of like dividing it by half each time, maybe even doing it further. Or it seems like you have to keep the sort of progressive process can be. It seems like it could be a little slow. Have you explored any of that? During your trading runs for distillation, or is that something that you have any information about?
No conclusive thing yet. But an easy thing to do is to actually start from, because DDIM works quite well with 64 or even 32 steps. So you could just start from that, use that as a teacher, and then it's not that intense of a training. So that's like the easy thing to do. But then also maybe doing like a different schedule of progressive distillation, as you mentioned. This might also be interesting. There are quite a few things you can try. You could also try using a different sampler than DDIM. So yeah.
Yeah, if maybe people, if anybody else has any other questions, otherwise,
Yeah, I had a question. Was there any particular difficult challenge you ever came when working on this? Yeah. One that really sticks out.
Do you mean for text to image or?
No, I meant yeah, any, well, it was just a very generic question, sorry.
Okay. Well, outstanding challenge. I don't know. I'm still a bit frustrated that we discovered classifier free guidance so late. This is when I first implemented it and just looked at the same model, but then sampled with classifier free guidance. I basically couldn't believe how good these samples are. It was with the ImageNet model. I mean, this was not really a challenge. Some papers mention it, but it was just like kind of very simple to actually implement it, but then it was changing everything actually. So yeah, I don't know. This really stands out to me as a moment where you realize, oh, this stuff really works actually. Yeah, I don't know. Other than that, it was like there's so many different like small things that you have to get right in combination. Like finding the right, like as I said before, like finding the right weighting with this adversarial training, and then going to that, maybe to that adaptive formulation. Then kind of finding this, we have like this rescaling of the latent space, and if you don't do that, you have like, you can end up with very different behavior actually of the model. So initially we did like this convolutional sampling of like these landscape images, and they looked really good if we did that in a VQ space, but it didn't look good if we did that in a KL space. And we thought, oh, is there some property of this VQ space actually? Until we realized that no, it's not. It's just like the KL regularized space is just has a very different variance than the VQ space, and because we use the same schedule, we actually had like different diffuse or denoising processes, and that influenced the final result quite a bit. And if we then just rescaled that, this effect went away. So this is yeah.
This is a figure, right?
Yeah, exactly.
Yeah, so without scaling, I guess you got like less diversity. Is that what's happening, or?
And less quality actually. These are kind of
okay,
blurry, grayish. I would even say it doesn't really work. Yeah, but this was yeah, this took a while.
Someone is asking how to solve the fingers problem.
Maybe pixel models can solve them, right? Maybe that's something that humans are very sensitive to. I think it's a combination of different things actually. So this is at a scale which is kind of, it's the same with faces at a certain scale, human faces at a certain scale. So scale where it's kind of hard to get the details right, and then also humans are extremely sensitive to that. Obviously, if you have like a large frame with a hand and it still has 6 fingers, then that doesn't apply. Yeah.
Yeah, and maybe pixel diffusion, like you said, pixel diffusion, because of course the Deep Floyd model, it seems to have pretty good fingers, but I think theirs is a pixel diffusion. Not entirely sure, but yeah, that's so maybe that may be definitely part of it. Yeah, I guess it probably has to do more with maybe that has more to do with the VAE in terms of like, yeah, this is the VAE. I guess maybe that's something have you analyzed that before? The VAE, whether or not it captures the fingers well.
So at a certain scale, it has problems. I mean, this is, but if you have like, let's say, this scale, then it should actually work. But I keep seeing examples where it doesn't work. So that's, I would say this is not an issue of the VAE then. more of a maybe of the data that it's trained on, not enough hands and on the scale, maybe not enough capacity to get this right. Different things. Counting is hard.
I was interested in hearing more about the architecture of the unit, or whatever. Not a lot of papers seem to go into a lot of detail about architecture. I was just interested in your thoughts on like whether you think there are opportunities to, well, kind of what you tried architecture-wise, and whether there are things you think haven't been explored enough, and also your thoughts about how conditioning is added to the architecture, like kind of adaptive group norm versus more of a transformers style thing. I'm particularly interested because I'm looking to kind of construct a reasonably high quality unit architecture with conditioning, but also one that's not too complicated so that my students could, understand all the code and fit it in their head.
I like I like cross attention quite a lot because it's so super simple, and you can just process everything with it. So in terms of simplicity, I think it's, and expressivity, I think it's very good. So okay, yeah, we basically started from OpenAI published the ADM model, and they published a code for that. We basically started from that architecture, and then we kind of did two things to condition on all kinds of things. So like there are two different classes of conditioning. One is spatial conditioning, like a semantic map, and then we basically just concatenate the inputs, and they can just use the architecture as it is. Or you have like some sequence which you condition on, and for that we introduced these transformer blocks within the UNet. And these transformer blocks are basically self-attention, feed-forward layer, cross-attention. Self-attention, cross-attention, feed-forward layer. And so this is basically like a mini transformer within that UNet. And with the cross-attention, you can just condition on any sequence, which can be a text embedding sequence or something else. And I think this is actually, it's actually simple enough. From the whole architecture is a bit, the whole architecture is a bit complicated or convoluted. And there are like two recent papers that I really like. One is the DIT paper, which is basically just a transformer. They do latent diffusion on ImageNet, and it's basically just a transformer architecture. They look at different sizes, at different patching factors to kind of map the input into the transformer embeddings, but then it's just a transformer. And this one is really simple, really cool. And then there was another one, RIN, or RIN, which I think they didn't publish code. It's more like a perceiver style architecture where the model is basically, it takes in the input and has some latent space, maps the input with cross attention to the latent space, applies some self attention layers on that latent space, then writes out again, and then you can repeat that multiple times. And this is supposed to be very efficient. I didn't try it yet, but I'm actually kind of excited about it. I really like it. I want to try it. I can also share a link to that. I think we also briefly talked about that.
Yeah, we've talked about that, and then the ADM paper we've covered in this reading group also. The DIT paper, yeah, I think we might cover that soon. Seems like a very interesting paper, so we might cover that soon. Yeah. Yeah, I think the ADM paper was one of the few papers that seems to actually more systematically analyze the architecture. I feel like the other papers kind of just like they just said that they did this, and they just talk about it in the supplementary material too. They don't even really talk about it in the main text either. So I think that was an interesting paper for sure.
Although even in that one, the unit itself was kind of taken as a bit of a given. They only explored some things around where and how to add attention or how much or stuff like that.
I'm also interested in exploring maybe like hybrids between pure transformer and the one that we're using. So you can easily imagine going from one transformer block at each level to multiple transformer blocks, make it kind of more transformer-like, but still have some convolution in it. I mean, there are lots of these hybrids in for like vision, so of like classical vision tasks. So this might also be interesting, especially in the regime where you don't want to go to extremely large scales, where it still should be in a kind of low parameter regime.
Okay, I think there's one question we may have missed from Nev, who was saying, have you tried distilling into a 20 billion model for one-step sampling?
No.
I think he's mentioned this idea to me before as well, I think. Thank you, Robin. Yeah. Yeah, I guess his idea was like you could probably fit in kind of like multiple steps within a single, like, over parameterized model. It might be able to kind of learn that. I think he was mentioning something like that.
Oh, okay, I see. Yeah,
I mean, I think such an idea, like replacing a multi-stage model with a single stage, always seems like a bad idea to me, because when you do a multi-stage model, it works like boosting, so you get multiplicative improvement for a linear addition in time steps. So in general, with boosting style models, such as iterative refinement models, such as diffusion models, doing a few steps of a smaller model ought to give you better results faster than a single step of a bigger model, as far as I can tell.
And so changing the size hasn't really been explored, so.
Like model size?
Yeah. Like distilling. Usually you would probably try to distill into a smaller model, but doing the others. Yeah. I don't know.
Yeah, I think the people have tried that for like classification and stuff like that.
Yeah, exactly. But yeah,
I mean, for generation stuff, yeah.
Yeah, in a diffusion context, it hasn't really been like for autoregressive. Sorry, for autoregressive models, it works quite well. But yeah, might be interesting.
Cool. If no one else, I guess, does anyone else have any questions? Oh, yeah, someone was saying, I guess about iterative refinement. If maybe a smart solver finds shortcuts, I don't know. I guess I don't know exactly what you mean. Maybe if you want to elaborate on that. The Jiminy's comment, the SD solver. Like you mean like it just? I mean, I don't know I don't know what you mean by finding shortcuts.
Okay, I'll see if I can try to explain what my thought is on that. So is it? We're thinking that for a diffusion model, we're always just we're iteratively refining, so sort of going from worse to better, one step at a time. But if we're using that reminds me of the DDPM sort of style. But if we're using stochastic differential equations to guide ourselves through a latent space, we're not always having to go each step getting better, next step better, next step better. Perhaps there's ways to go through the space where the next step is worse, but the next step after that is even better than having gone 2 steps iteratively. You get what I'm saying? So taking shortcuts through that space via a very clever solver, as opposed to just trying to slowly iterate away the noise.
I'm not sure if that ever happens. I don't know.
Well, it does in a sense of like Langevin dynamics itself is like we add noise and we take it away. We add noise and we take it away. So we're actually making it a bit worse than making it a bit better. Making it a bit worse, making it better. We're not just going each step going from worse to better in a linear fashion or an iterative fashion.
But you're still adding less noise than you had at the beginning. So each individual step is slightly better than the previous one.
Say that again?
I mean, the
Like-
current approaches are definitely inefficient, which is why I said like boosting related techniques and diffusion models are not quite there yet. They get closer once you distill them, but they're still training, well, they're still doing inference on out of domain images, by definition, because they were never trained on partially reverse diffused images. But in general, if you've got something which can improve a model, and if you run it again, it improves it more, and it runs again, it improves it more, you have, to me, a framework for basically for doing boosting. And in that framework, you should be able to get multiplicative improvement with each step, and each step adds linear more time. So to me, like our goal should be to get really good iterative refinement approaches rather than really good single step approaches, I guess is what I was trying to say. But I do think the current iterative refinement processes clearly have room for improvement, which is something hopefully we're slowly working towards.
Yeah. Okay. So yeah, I hope that, yeah, I think that addresses the question. Yeah. Progressive distillation slowly improves them and creates shortcuts. You mean like that's what you think progressive distillation is doing, like just making it more efficient at solving, or? Yeah, Nev, what do you mean by that? I don't know if you're talking, but I can't hear you. Oh, I don't know. Okay. Yeah, progressive distillation was related. Yeah, I guess, yeah, I mean, yeah, I guess what Jim is saying is needs to be, yeah, it's still there's efficiency. Like the current solver still may not be efficient enough, and yeah. Yeah. Robin, do you have any thoughts on this, or?
Not really. Like maybe another way, another line of thought is the LSGM style of motivation, where you kind of create a space, or you regularize the diffusion in a way that, the diffusion process in a way that it is more linear or has nicer properties from just by default.
Yeah.
So I think this one might also be interesting.
That's a good point. Yeah. Yeah. Do you think that the latent space right now, I mean, that probably already kind of encourages some form of linearity, or?
I don't,
because I mean,
really...
it's pretty because I mean, some of these samplers are pretty efficient, right? So I thought maybe that's part of the reason why, or is it a different reason why?
Yeah, I was wondering the same, actually, because some of these solvers are actually very efficient. That's true.
Yeah.
But they might also be a bit over-engineered towards that specific space. So, right.
I guess for the VAE, I think that part of it is just like also like a random points in the VAE space a little bit closer to a regular image, maybe. I think that's also part of it. Like it's more compact in terms of the latent space.
Yeah,
it's easier to.
definitely. Yeah, definitely. This is kind of the basic motivation also, but
So
yeah. But I mean, this space is still kind of not much. There's not much regularization happening, right? So, I mean, if this is already enough to make it efficient for these kind of samplers, that's super cool. But I think there's more that you can do. The difficult part is how do you kind of keep the high quality that you want, because this is always this trade-off that we were also talking about with this other paper. Yeah.
Something that really surprised me with diffusion models is the way, even when we don't use latents, that we can kind of get away with just using MSE. You know, because traditionally with one-step models using MSE, you would end up with out of focus, blurry things. I understand why we use MSE. It's because, you know, it's in the mathematical formulation, you know, it kind of falls out as matching the, you know, score-based or Langevin dynamics processes. But I guess my question is, like, if you looked at, like, have you tried other loss functions? Like, because we've kind of, despite the mathematical foundations, we end up throwing them away anyway. We don't actually follow what the formulas say we're meant to do because we find some other things work better. I'm wondering, like, have you tried using like perceptual loss in addition to MSE? You know, in the diffusion process, I know like it's a little bit like more difficult to do that in latent space, but you could even do that in latent space if you trained a model which took latents and did classification on them, and you know, you could then have perceptual losses. Yeah, so just curious if you've looked at different loss functions.
Yeah. Perceptual loss might be interesting. We didn't look at the perceptual loss. We tried L1 loss. We tried in the VQ space. We tried adding like a discrete token prediction in addition to the continuous regression. So we played a bit with this stuff. In the end, we didn't really do it. You know, like we didn't have like a result where we thought, oh, this is working much better, and then we focused on that. So we just stick to the MSE. But yeah, I agree. Especially something like perceptual loss might be interesting, and you could also do it by decoding. Then it gets more expensive, like going through the decoder. But on the other hand, there are also like this very cool linear mappings from latent space to pixel space. So you could also make use of that to apply the perceptual loss. Yeah.
Well, and the thing we experimented with, where you trained for us the 4-channel version with the first 3 channels.
Yeah, exactly. Yeah. I have to relook into that actually. yeah, I agree. I think perceptual is interesting.
But either way, you don't need to decode, right? Because as I was saying, you can train a ImageNet model or whatever, which takes as inputs.
Yeah, absolutely. Yeah, absolutely.
Kind of like Jono's mid-U idea, you know.
Then the question is, do you want to train this extra model, and then if you want to change the architecture, then you have to train another model. Like if you want to change the latent space, you have to train another model.
But training an ImageNet classifier is trivially easy nowadays compared to all the other stuff we do.
Yeah, okay. Okay, that's fair enough.
Have you ever like considered like just recreating the VAE, because you're still using the same one from the late diffusion paper?
There are quite a few new VAEs actually. It's
I know, of course, Catch has released her decoder, but I was thinking like, what about the encoder too? Like that probably should.
Yeah, absolutely. Yeah. This is this is like super easy to. So if you want to stick with that kind of training paradigm, then yeah, I would say. So if you want to train a new model, train a new autoencoder, train a better one. It's possible. Yeah, definitely.
It's trained on a different data set altogether. It's like completely different. So I thought
This is from open images, but it works. But
yeah,
definitely,
it works, but it's just,
definitely, yeah, very, very low hanging fruit to improve on that.
Yeah. Okay, yeah. I mean, if any other questions? If there are no other questions, then yeah, I think we're done for the day. Thank you, Robin, for joining us. I think this was a very insightful discussion. I found it very useful. I hope other people found it useful too. Yeah, thank you for joining us. And yeah, I'll send information to the rest of us about the next reading group and stuff over Discord. Yeah, so
okay.
Have a great weekend and talk to you guys later.
You too. Thanks for inviting me. Bye bye.